Jnanam paramam dheyam. Knowledge is supreme.
Okay. Now, in the previous section, we have performed a discussion of time dependent perturbation theoretical treatment of a two-state system characterized by wave functions psi L and psi m. We are more or less working with the understanding that psi L has lower energy, psi m has higher energy, but it can be the other way around, it does not matter. In doing that, if you remember, we have written the wave function of the perturbed system as a linear sum of two wave functions, where Cm is the coefficient of the state that is not populated at 0 time. Okay? So, if you are talking about absorption spectroscopy, the higher state. And we have derived this expression that dCm dt is equal to minus I by h cross an integral over space multiplied by an exponential term, an exponential factor in time. Now, the next step is to use the expression for the first order correction to the Hamiltonian, which is this. Well, actually this multiplied by minus mu x, okay. Put it in there and see how the expression evolves, okay. That is what we are going to do now. Yes, yeah. How do we get the Hamiltonian as minus mu x into Ex? All right. So, the question is, how do I know that this Hamiltonian, first order term, does that answer your question? Okay. So that one was missing. How do I know that the correction term is minus mu x into Ex? Because if you remember how this wave mechanical treatment of quantum mechanics is carried out, we always start from classical mechanics, don't we? Right? When you worked with the harmonic oscillator, for example, how did you write the Hamiltonian? You wrote the Hamiltonian, well, the kinetic energy part is the same anyway, but for the potential you wrote half kx square, right? Where did we get that from? We got that from our understanding from classical mechanics that for a simple harmonic oscillator half kx square is the potential energy. Here also we are trying to think how we can model our system. So, building model is a very important step in any theoretical treatment. What is the model that you want to use? Of course, then the question that comes is that is the model correct, or does the model apply, and if it does, how far does it apply? So, the model we are using here is that we are modeling this molecule as an electric dipole, okay, and we are only working in the x direction, so mu x. We are modeling light as an oscillating electric field, we are neglecting everything else. Why? Because this electric dipole electric field interaction is going to be the strongest among all the interactions that are possible within this model. You can start with x, y, z, does not matter, okay. What we will do is this, we will get some expression for x direction only. Now, do you think for an isotropic radiation means in all directions you have oscillation. For isotropic radiation, you will get the same expression, right, for Ex, Ey and Ez, right, then it is very easy to combine them. That is what we will actually do in the next class, okay. A factor of 3 comes in, that is all. Any other question? Any other question? Okay, good. So, let us tidy up this a little bit before we go ahead and put it there. What is the first order correction term for the Hamiltonian? It is minus mu x into Ex, of course, we will now write the expression of Ex into 2 Ex 0 into cos 2 pi nu t. All right. Now see, this is what is going to go in here. All right. And what should we try to do? We should try to separate the factors, right? The one in spatial coordinates and one in temporal coordinate time. So, I think you can see from this expression and that expression that it appears that the problem should become simpler if we convert this cosine term, cosine factor to exponential terms, sum of exponential terms, because I already have something that is an exponential term in time. Okay. If I write this cosine in the exponential form, then it should become easier to handle this problem. Okay. So, see, please understand the line of thinking. This part is sometimes intimidating for us chemists, because we see a lot of algebra, and what we tend to do is we tend to remember all of it. Alright. That being said, and now we have to be careful, because this is the point where my derivation and Graville's derivation become different. Okay. So, what do I write? Minus mu x Ex 0. What is cos kt? E to the power I kt plus or minus e to the power minus I kt? Sure? Plus, and is there an I multiplied somewhere? No, that is for sine. So, it is something like this, and is there a half, right? Yes. So, I can just do it step by step. 2 Ex 0 multiplied by half e to the power, I will write like this, exponential 2 pi I nu t plus exponential minus 2 pi I nu t. Is that right? Is that right? A whole by 2 I have written already. You cannot read it only because my handwriting is bad. 2 Ex 0 multiplied by half. Okay. Of course, this 2 and that 2 thankfully cancel off. So, I have one, it sounds very strange if I say I have 1 2 less to think of. Anyway, is this expression correct? I will modify this a little bit and I will modify that a little bit also. So, what I do is here instead of h cross, let me write it completely as h here and 2 pi here. What am I trying to do? I am trying to make these two expressions completely compatible. Here I already have 2 pi, right? So, why do not I divide by h and multiply it by h? Why did I do this? I did it so that the two expressions look similar. So, it becomes a little simpler for us in the next step. Also, here now I have h nu, here I have h nu and E are of the same dimensions, right? Okay. So, just demonstrating that these two are actually dimensionally consistent, there is no problem. Let me now write, there is 1 minus 1 here and 1 minus 1 here, multiply 1 by 1, it becomes plus 1, right? Right or wrong? According to Graville, it does not. So, this is where the difference begins. Okay. I divided by h cross. What else do I have here? I have Ex 0. Ex 0 is a constant, right? Ex 0 is a constant, so I keep it here. I will put mu x inside the integral, because as you have seen when we derived the selection rules for your vibration and rotation, mu x can actually take up different terms for different problems. So, I cannot keep mu x outside the integral, I have to take it inside. So, when I do that, this is what I get. I am taking mu x inside, so I write psi m mu x psi l integrated over all space. Does that look familiar? What is it? Yes, that is our transition moment integral. That we have been seeking so far. We wanted to know where transition moment integral came from. Now you know the answer. Transition moment integral came from this time dependent perturbation theoretical treatment of transition between two states. Okay. Even before I write the remaining terms, remaining factor, tell me this, what happens when transition moment integral becomes 0? Cm is equal to 0, step by step, do not jump steps, right. dCm dt is 0, right. You start with Cm equal to 0. So, this is what we are saying, Cm versus t, initially it is 0, this is 0, 0 point, right, and initial time it is something like this. So, if dCm dt is also 0, then after any time t you do not reach anywhere, right, your Cm remains 0. Okay. So, that is why we have been talking about transition moment integral in our previous discussion. If transition moment integral is equal to 0, then the system remains in the lower energy state, or rather the initial state characterized by L, quantum number L. There is no question of it mixing with the state characterized by quantum number n. Okay, dCm dt equal to 0, and we will come back to it and put it in a little different way, actually it is the same thing a little later. Great. So, this is your transition moment integral, fine, multiplied by, now I have two exponential terms, right. First one is exponential 2 pi I by h Em minus El, what do I do, plus h nu, right, h nu multiplied by t. Have I written it correctly? Because I also get confused when there are too many brackets. Have I closed the bracket in the right place? Okay? Then I can write the second term, plus e to the power 2 pi I by h Em minus El minus h nu t, close second bracket, close third bracket. Is this correct? Is this correct? Shushnato, correct? Can we go ahead? Have you understood all this? Any question, Vikas? No question? Very good. Okay. Now, we need to understand what these functions would look like. But before that, maybe let us do the integration. So, this is the first integration that we promised to do today, and this is where I get an answer that is different from this Graybill. So, I want you to do it. So far you agree with me, right, whatever I have done. Now, what I want is, I want to know what is Cm How do I get a value of Cm? Your derivative is known, okay. So, Cm would be what? Cm0 plus this multiplied by whatever changes. So, basically you integrate the right hand side with respect to time, and when you integrate with respect to time, what are the limits? 0 to t, exactly. Can you do the integration and tell me what the first term turns out to be? What? You are saying that because you know Bohr resonance condition, okay. Right now let us say it may or may not be equal to 1, okay. Let us say this is a constant, forget what it is, some constant k, alright. With that let us do the integration. So, what Manthan is saying is actually correct. What he is saying is the second term, in the second term we have Em minus El minus h nu, isn't that equal to 1? It is equal to 1 when Em minus El equal to h nu. But then even here this is also equal to 1 when El minus Em is equal to h nu, right. So, we will talk about that. That is actually what brings us to the second important aspect of this discussion, that is Bohr resonance condition. But before that, please do the integration and tell me what you get. Meanwhile, I will just go ahead and write this. Shobana, what's the answer? You are getting negative of this, right? I also have got negative of it, but I do not know why in Greville this is the expression that is given. It does not matter, I can always write a minus sign outside. And what happened to this H cross? That got cancelled during integration, right? So, for now what we will do is we will go by Greville's expression, because it does not really matter. My expression really has that minus sign outside, and it looks like you are also getting that. What about you, Manthan? Okay. Just tell me, do you get this or do you get its negative? You get a negative. Okay. Let us just go with this expression for now. Let us not bother about the minus sign outside, because as you will see, eventually we take mod square. So, we do not have to worry about minus. What is the second term? Plus 1 minus exponential, what happened? Minus 1 aa raha hai na? हाँ, वो मेरा भी वही आ रहा है. But then Greville has written the book, not I, not you. So, we will follow we will follow it, but it does not matter. That is the point I am trying to make. You can write a minus sign outside, it does not matter, because eventually what is important is your mod square. Of course, physically what it means is that dCm/dt can never be negative, isn't it? dCm/dt has to be positive. So, that is the only place where I have a little bit of a h. Anyway, we will just continue from here. 2 pi I by h Em minus El minus h nu t divided by 2 pi I by h Em. I do not have the 2 pi I by h. Em minus El minus h nu. Yes, because we have cancelled the h cross. So, this is okay except for the minus sign. Let us proceed with this. Now, look at these two terms. Will you agree with me if I say that most of the time both the terms are actually very, very close to 0? Will you agree with me if I say that? We are dividing by h, right? Here, dividing by h here means what? H is a very small number. What is the value of h? So if I may digress a little bit, a very favorite question in BSc that was there when I was a student, I do not know if it is still favorite, is that what would happen if h was equal to 1? So, if h was equal to 1, then this, what is the product of uncertainties? That is h by 2 pi, right? So, the problem is that uncertainty would enter the real world, macroscopic world, not real world, yeah, macroscopic world. So, everything u, I, chalk, board, everything would be uncertain, right. So, thankfully, h is not equal to 1, h is a very small number. So, because of that, what happens is that the fall off of both the exponential terms is rather sharp, okay. We can safely say that both the terms are actually equal to 0 unless the denominator is equal to 0, okay. If the denominator is equal to 0, then what will happen? The term will blow up, right, okay. So, first thing is both the terms cannot survive together, because the conditions for blowing up is Em minus El is equal to h nu or El minus Em equal to h nu. Of course, both cannot be satisfied at the same time. H nu, is that positive or negative? H nu, frequency is always positive, h is a universal constant, that is also positive. So, right hand side is also positive, is always positive. So, that means left hand side has to be positive. So, what does the first one mean? Em minus El is positive, that means El is smaller than Em. Okay. What is the step that is, what is this the level that is populated at 0 time, L or M? L. क्या बोल रहे हो? L बोल रहे हो, अच्छा ठीक है, L, M, anyway, L, right? L for lower. This is the situation in that case. For first one, Em minus El equal to H nu, this is Em, this is El. For the second one, the upper one is El, the lower one is Em. Okay, and I will just draw the arrow to indicate the nature of transition. So, the first one, Em minus El equal to H nu, well, it is a little strange because this is actually the second term, right? Em minus El equal to H nu, that is satisfied by the second term, not the first one. Em minus El minus H nu equal to 0. So, when Em minus El minus H nu equal to 0, what we are essentially saying is that we are dealing with an absorption. The transition is absorption, going from lower to higher level. When El is higher and Em is lower, we are saying that we are dealing with emission. That is all. Okay. So, this term is going to blow up when we discuss absorption. This term is going to blow up when we have emission. Right. But the point to note is that for absorption as well as emission, the terms are exactly similar, right? Is that right? 1 minus e to the power kt divided by k. You can write both in the same way. It is just that k is different depending on whether you are talking about absorption or emission. Same kind. So, please remember this. Please remember. So, what I am trying to say is that the expression for Cm for absorption and emission should actually be same, isn't it? Because e to the power kt by k, that is all that is there. Understand what I am saying? Well, 1 minus e to the power kt by k, that is the general form that is there for absorption as well as emission. So, the Cm, or later on when we talk about Cm star, they should have the same kind of expression for both the processes. The only thing that we have to remember is that when we talk about absorption, I mean induced absorption, of course. What is the meaning of induced here? Induced mean something that is brought about by external light. Second part is perhaps a little more difficult to understand. When I talk about emission here, I am talking about induced emission or stimulated emission. Emission that is brought about by presence of light, not spontaneous emission. As you know, if you excite something, many times it just gives out light by itself. It has to come down. We are not talking about that kind of emission here. We are talking about induced or stimulated emission. Please do not forget this. This is a very important point at this juncture. Okay. So, well, I had promised 2 integrals today, but looks like we'll have to be satisfied with 1 because our time is almost up. Let me just write the final expression. So, what do we deal with? Which one do we deal with to start with, absorption or emission? We will deal with absorption. Absorption happens first, emission happens subsequently. So, for absorption, the expression for Cm turns out to be then 1 minus, well, I should write the whole thing, Ex0 multiplied by your transition moment integral multiplied by one minus exponential 2 pi I by H Em minus El plus H nu, no, minus H nu, sorry, multiplied by T divided by Em minus El minus H nu. This is the closing expression for today and opening expression for the next class. What we will do now is that we are going to take this Cm. Cm gives you amplitude, okay? Amplitude of what? Psi m, capital psi m. Now, if I take mod square of that amplitude, do you know that this mod square of amplitude gives me the contribution or probability? Yeah. So, we want an expression for mod square of Cm. That is what we will work out the next day, a little more algebra, that is all. And then we are going to reach another important observation. What have we learned today? Let us summarize. We have learned two things. We have understood where transition moment integral comes from, and we have understood that Cm is 0 if transition moment integral is equal to 0. Cm equal to 0 means there is no mixing of states brought about by light, or in other words, there is no transition brought about by light. That is the first important thing that we have learned. The second important thing that we have learned is Bohr resonance condition. We have seen that unless Bohr resonance condition is fulfilled, you cannot have an induced transition, may it be absorption, may it be emission. Okay? We have been taking Bohr resonance condition for granted so long, and it makes sense also, right? Even without doing any math, it makes sense if we say delta E equal to H nu, we can understand it from our common sense. But what we see is that we can arrive at using uncommon sense as well. Okay? So, these are the two take home messages for from today's discussion. Next day we are going to talk about mod Cm square, and then we will get access to one more thing. See, so far whatever information has come is from the space part, right? The time part has given us one information, that is your resonance condition, but there is something more that will come out from here. From here we learn that what kind of system are we talking about so far? How many levels? 2 levels. What are the energies? El and Em. So, what kind of spectrum do I expect? One line, right? One line, no width. When we do the rest of the math here, we will see that even for this system where you have El and Em, two energies, you can never have a 0 line width. Some finite line width will always be there, that will come from the time part, right? And that is what is going to be related to your uncertainty principle. So, that line width that you get is called natural line width. Okay? This is what we will discuss the next day, and then we will go on to what is called your Fermi's golden rule. Okay. And we will also talk about the Einstein's discussion, and we will see what is the relationship between the different absorption coefficients. Okay. This is what it is for today.